I used to think quantum computers were just this kind of sci-fi dream, something in the future. And computing obviously has come such a long way from its inception. Could you share what a quantum computer actually is, what that means, what it's capable of?
Yeah. So indeed, there's a lot going on around quantum computers today, but the idea actually comes back to the end of the 70s, early 80s. We didn't have the technology there, but that's when the theory really got started. A prominent physicist who talked about this idea was Richard Feynman. He won the Nobel Prize in Physics. He posed some of the first principles of quantum computing, how you could make computations with quantum mechanics. And now what we're trying to do is actually bring that into reality. So these quantum computers are composed at the very end of what are called qubits, which are the analogous of classical bits, which can store ones and zeros. But these qubits can store a myriad of other possibilities. Okay. And it's in that myriad of other possibilities that you can get the large amounts of computation. Of course, there are challenges. Making stable qubits and that don't fade away with noise is extremely difficult, and probably that's the biggest challenge at the moment. That's where the software that we're writing right now comes in trying to control these qubits to keep them stable as long as possible so they can actually do something useful.
What are some of the possibilities that it could bring to life in terms of achieving different computations?
Yes. I think I should start by saying that there's a bit of misconceptions in terms of quantum computing. Some people think that this will actually replace the computers we use today. That's not true. It will be a complement to classical computers. So it will not substitute them, but they will be dedicated to solving very particular problems. Especially problems where you need to try hundreds or millions of possibilities quickly.
Yeah.
This is where quantum computing really excels because, as I said before, a lot of possibilities can be encoded in a single qubit at the same time. Yeah. So the values that it can store at the same time are infinite in theory. And therefore, you can search and compute with much more values in less time. So, for example, optimization problems where you need to search a lot of possibilities, what's more optimal, what's not, based on hundreds or even thousands of variables. Then quantum computing can be here to actually compute all these possibilities rather quickly, which a classical computer could take years to compute.
Yeah.
Machine learning, where you need to explore data, create models, taking into account thousands of variables or hundreds of thousands of variables or millions. Quantum computing can help there as well. These can further be applied in industries like finance, logistics, mathematical modeling, scientific research, etc., etc.
And since you say it's more of a complement to everyday computing, do you think it could be quite a practical thing in the near future that although it won't replace normal computers, it will be quite common or widespread?
Not at the moment. Right now, it's quite experimental and very new. And again, there are a lot of challenges to make it practical. At the moment, the only quantum computers that exist are in labs with extremely well-controlled temperatures that almost reach absolute zero. These need to be controlled and manipulated with lasers or microwave pulses. Wow. So it's all these big refrigerators just to store a tiny little chip. But it takes a big refrigerator, control with liquid nitrogen and so forth to make it work. So at the moment, it's just experimental. They live in laboratoriums. It's not practical yet, but as all of technology, right? It begins this way.
Sure, just like the first
current computers began this way.
Yeah, exactly.
As very big building size computers, which then became smaller and smaller until you have a cell phone in the palm of your hand. So technology starts this way. Quantum computing is just at the beginning. So it's rather expected that it is like this. As years go on and time goes on, I think there'll be good progress made. I cannot make predictions of when it will actually become
that was going to be my
a household item. But maybe practical uses are not that far away. 5-10 years perhaps. Still carried out in labs, but solving already important problems. Right?
So maybe not a household item, but maybe businesses could start using it for improving their customer experience, for example.
For example, cloud services, they could have their quantum computers in their own installations, right? And just hire it over the cloud to solve specific problems. That's how I think it'll start. It won't be a quantum computer in your house, perhaps.
Well, maybe one day. That's really fascinating. Surely there's also quite a few risks that come with that post-quantum encryption.
Yeah.
Could you explore that idea and what it means, and are there any potential risks?
Yes. So as with every technology, of course, you could use it for either good purposes or bad purposes. I mean, you could say that of fire even.
Yeah.
So quantum computing is not the exception. One of the areas that's being explored is indeed encryption, because current methods of encryptions are based on the fact that finding the solution to the encryption problem takes millions of years for a classical computer. There are just so many possibilities.
Like with passwords.
Yes, with passwords, but this one even more difficult because they are mathematically complicated using numbers that are hundreds of thousands digits long, multiplied with several operations and cycles. So you need to find the right combination of these numbers to actually being able to decrypt the key. It's extremely difficult and takes a classical computer millions of years to solve. But as I said before, with quantum computers, these qubits are able to encode a myriad of possibilities at the same time in the same qubit. So it's calculating all these possibilities at the same time, or at least in theory is able to do that, which means that guessing all these combinations of numbers and operations to unencrypt your key, basically in a brute force way, could be done realistically within a time that is actually threatening to your bank
New
accounts.
Security concerns.
Yeah, exactly. That's why part of the research that's being done in quantum computing is what are the ways encryption can be enhanced to avoid this. So that's what we call post-quantum encryption. So encryption schemes that will be able to withstand the computations done by a quantum computer.
That's a very real risk, isn't it, for us? And one that has to be solved because, like you mentioned there, banking. People's money sits on top of technology that utilizes what you're referring to there as like the sort of the current encryption, whereas quantum computing would be able to solve that within a shorter time frame, exponentially quicker time frame, let's say.
Certainly. Or communications, your WhatsApp, your Signal Messenger. These are all based on the principles of encryption. If these are broken, then your communication is exposed.
What do you think are the first uses of quantum computing that we will see?
One of the first applications that's already going on is quantum communication, where you can really entangle two particles and actually make them communicate, qubits, entangle qubits. This communication is ultra secure, right? Because it's based on the principles of quantum mechanics. That means that an eavesdropper will disturb the state, making it impossible for the communication to go on further. So they are already testing the first quantum network to make this type of communication, and they are already deploying the first prototype of this. And the other application that's already going on is modeling molecules. For example, when you want to create a specific type of medicine, at the very molecular level, these are based on shape, how proteins fold and how they match with each other and so forth. It is extremely difficult. It is a rather difficult problem to solve with a classical computer. Quantum computers, which already work with quantum principles that are the ones at play on the molecular level, they can solve these problems much more easily.
Okay, that makes sense.
So, and there's already papers and literature on how this could be solved, at least in theory, once these qubits are there and find out new molecules for therapies. This will come into play for finance, for example, calculating risks on real time, using worldwide data, and at every moment calculating your risk and knowing your risk position, extremely valuable. Logistics problems on a worldwide level, shipping, commerce, these are all applications that are already being thought of.
Space travel?
Space communications.
Communications, okay.
Travel, maybe not yet.
Well, yeah,
but space communications, I mean, the Chinese already have a satellite that uses quantum communication.
A lot of applications coming in.
Yeah.
Watch this space.